Hi guys, this is Mrs. Allison. Today we are going to look at the first derivative test. So what I would like you to do is, before we begin that, try your warm-up that's on the notes. So hit pause, come back. Okay, so we can see from here that this figure shows two parts of the graph. It doesn't mean it's the whole graph. I'm just showing you bits and pieces of the graph of the function f of x that is continuous. Some of these key phrases that we want to pay attention to, that is continuous on negative 10 to 4 and differentiable on negative 10 to 4 as well. It so happens that the derivative is also continuous on negative 10 to 4. Okay, so the first question says, explain why f must have at least one zero from negative 10 to 4. Okay. This kind of goes back to that quiz question that you guys had before when we need to explain, and I said some of you need to state the theorem. This would be an example of that. What we would say is that when we plug in negative 10, oops, I did not want to use the marker. Let's go back to the pen. If we do f of negative 10, we can see that that is greater than 0. We can see that from our graph, f of negative 10 is greater than 0. What we can also see is that f of 4 is less than 0. And since f of x is continuous, by the IVT, there is some number c that falls between negative 10 and 4, where f of c has to equal 0. Okay, so that would be an explanation or a justification. All right, well then the next question says, explain why the derivative must have at least one zero between negative 10 and 4. Okay, so when we talk about derivative, we need to look at the slope of these lines. So for example, if I look at the slope of this first piece right here, so if I look at the slope of this first piece and I were to draw tangent lines or slope lines, we know that the slope, oops, we'll pretend that that touched, is in a positive direction. So my slope here is positive. So what I could say is that f prime of x is greater than 0. Okay? And then if we look at my the second part over here, and I look at the slope over here, what I can say is that this slope of this line, or the derivative, is going to be less than 0. And therefore, I'm going to use similar logic. Since f prime of x is continuous, because it says that in my problem, by the IVT, by the intermediate value theorem, there is a c such that negative 10 is less than c is less than 4, where f prime of c equals 0. Okay, let's keep going. What we're going to focus on today is the first derivative test. And to be able to use the first derivative test, there's a few steps we're going to go through. We are going to find domain restrictions for our function. Then we're going to find the critical numbers. Okay, so this is important. When we find the critical numbers, we know that finding critical numbers, we did this yesterday, was taking the derivative and setting it equal to 0 and where it's undefined. But the problem is, if there's a place where it is undefined that is not in the domain of the original function, this cannot be a critical number. So that's why it's important to know what your domain might be, so that when you go to find your critical numbers, you know if what is undefined or a critical number might not be in the domain of the original function. Okay, then we're going to make a sign chart to organize the critical numbers and deal with the sign of the derivative of f of x. And that will then tell us the behavior of f of x. So we're going to list the increasing and decreasing intervals and or identify relative max min of the x value. Okay, so there's a couple key notes here. Sometimes questions are going to ask you for the x values where the extrema occur. Sometimes they're looking for the points, the ordered pairs where the extrema occur. Or sometimes they're just looking for the max or the min, which means they're only looking for the y value of the extrema. So make sure that you're aware that you're answering the question that is asked. That way you're not answering the wrong thing. So let's look at a couple of examples. Okay, so let's find the intervals on which the functions are increasing or decreasing, and find the local extrema. And then it says justify all points. So make sure that you have a reason as to why it is. A sign chart is not an acceptable justification when it comes to the AP test. Okay, so let's get started. So the first thing we want to do is think about our domain for this function. Whether you want to rewrite it, whether you want to look at it a little bit differently, what is the domain? Is there anything for x that we can't plug in? Well, this is taking a cube root of this, so it doesn't matter if I have positive or negative numbers. But with this x squared, no matter what I plug in, it's going to end up being positive. The x part here is going to be positive. This may still be negative. So I think in this case, it is safe to say that my domain for this function is all real numbers. So from negative infinity to infinity. Well, the good news about that is whatever critical numbers I find, those are going to be, in fact, critical numbers. I don't have to worry about throwing them out because of the domain. So let's take the derivative of this. So if we do f prime of x equals, we would get 2/3 x squared minus 9 times 2x, to the negative 1/3 power, times 2x. Simplifying this might help you to visualize it a little bit more. We get, positive 4x over 3 times, that'd be the cube root of x squared minus 9. Okay, so there's a couple places where this is going to be equal to 0. Where f prime of x is going to be equal to 0, first of all, is when 4x equals 0, because if x is 0, the numerator becomes 0, and if the numerator is 0, then the whole function is 0. So one of my critical numbers is 0. And then I need to look at the second part. I need to look at where the function is undefined. And this is undefined when the denominator is equal to 0. And where the denominator equals to 0, if we have 3 times the cube root of x squared minus 9 equals 0, really what I'm looking at when I go and simplify this is I'm just finding out where x squared minus 9 is equal to 0. So I would get x equals plus or minus 3 would be my other critical values. And it's okay to have those because my domain is defined for all real numbers. Okay, so I'm going to make a chart. And on my first derivative chart, I'm going to put my 3 values. I'm going to put negative 3, 0, and 3. And what I'm going to do is I'm going to look at what is happening within my first derivative in each of these intervals. So I'm going to try to figure out within each of these intervals what the sign of the first derivative function is. Okay, so on this first one, let's say I plug in, let's do negative 4. And if I plug negative 4 into this first derivative, my numerator will be negative. My denominator, well, negative 4 would be 16 minus 9, so that's positive. So I will have a negative number over a positive number. So this number is going to be negative. Let's just do that here. And then if I plug in a number between negative 3 and 0, so maybe negative 1, my numerator is going to be negative. My denominator is actually going to be negative. So I have a negative divided by a negative, which is a positive. And I'm going to repeat that process. If I plug in positive 1, we get negative. And if I plug in positive 4, say for example, we get a positive number. Okay? And so what we know here is that this 0, it's 0, whereas here, these values, it's undefined. Okay? So what does this tell me about my original function? If we go back to f of x, and I consider what's happening with f of x, well, I know if the slope is negative, then the original function is decreasing. And if I know if the slope is positive, my original function is increasing, decreasing, increasing. So I can get a rough shape of what the picture of this graph might look like. So what does that tell me about this function? Well, it tells me that there's several things happening. I know at this point where it goes from decreasing to increasing, right here, I'm going to have a relative minimum. A relative minimum because I don't have an interval to find an absolute minimum to deal with. And then I can see that same process happening right here. So both at 3 and negative 3, I have relative minimums. And then if we look at 0, I'm going to have a maximum because you can see as it goes up and then comes down, we're going to have a relative maximum right here. Okay. Now, I need to talk about increasing and decreasing. Well, we looked at that based on our slope. So what I would need to say, if this happened to be an AP question, what I would need to say is that f of x is decreasing, I'm going to abbreviate, decreasing on the intervals. Well, it's decreasing from negative infinity to negative 3, and I can say negative infinity because I know the domain is all reals. Negative infinity to negative 3, as well as 0 to 3. Because, why? Well, because the first derivative is less than 0. Okay? I can also say that f of x is increasing, and using that same idea, negative 3 to 0, and then with 3 to infinity, because the first derivative is greater than 0. Now, when we go to explain our max and mins, again, the sign chart is not enough information, so we might say that f of x has a relative max at x equals 0 because f prime of x changes from positive to negative. That would be your justification. We don't actually need to show the math for why we know it's positive or why we know it's negative. To justify a relative max, we would simply say that because it changes from positive to negative. So similarly, f of x has a relative minimum. Well, we have two values, x equals negative 3 and 3. And I'm going to use similar logic because f prime of x changes signs from negative to positive. Okay? That is our justification. So when it says to justify, that's what it would look like. Now, you want to make sure that it says find all local extrema points. We didn't actually take this into consideration yet, the fact that it's a point. Okay, so we know where the relative min and where the relative max occur, but so what do I want to do to figure out what the actual value of that is? Well, I want to go and plug it in to my function. So if we look at our minimums, we said we had a minimum when x was negative 3. And if I plug negative 3 into my function, I get 0 out in my original function. And if I plug in 3 into my function, we get 0 out. So my relative minimums are at the point negative 3, 0, 3, 0. Then when I look at my max, my relative maximum, we said it was when x was 0. And I'm going to take 0 and plug it in. So if I plug 0 into my function, we get negative 9 to the 2/3 power. So we get the cube root of 81. So this would be the cube root of 81. would be the y value. So these would be the max and the min in terms of points, whereas this is the justification as to why they are max and mins. So I would like you to hit pause, and I would like you to try this second example. Okay, on this second example, I'm actually going to scroll the screen just a little bit. Hopefully you see the domain is given to you from 0 to 2 pi. So though we need to make sure we pay attention to that as we go through and take our derivative. So if we take the derivative of this function, let's do, I'm going to write it in black this time just so that it stands out from the blue that's up above it. So we would get dy dx equals 1 minus 2 cosine of x. So I don't have any place where this is undefined, but I do have a place where the derivative is equal to 0, or I can find places where the derivative is equal to 0. So I'm going to solve this. So I get the cosine of x equals 1/2. So where is the cosine of x equal to 1/2? Well, we get when x is pi over 3 and 5 pi over 3. So now I'm going to go make a first derivative chart. And on here I'm going to put pi over 3, doesn't really need to be this big, and 5 pi over 3. I know at both of these places, my first derivative is equal to 0. So now I need to figure out the sign in each of these. So if we plug in something that's, say for example, 0, well we know that this, actually let's go and put that in, because the minimum value I've got here is 0 and the maximum I've got is 2 pi based on my domain. So let's plug in something above 0. Let's plug in, say pi over 6. If we plug pi over 6 into my first derivative, I would have 1 minus 2 times the cosine of pi over 6. So 1 minus 2 times root 3 over 2. So 1 minus root 3. Is that going to be positive or negative? Well, that's going to be negative. Similarly, if I go between pi over 3 and 5 pi over 3, so let's say just pi. If I plug pi in, if I do 1 minus 2 times the cosine of pi, the cosine of pi is negative 1, so 1 minus 2 times negative 1 is a positive number. And keep going, if I do it again, this is going to be a negative number. So if I were to look at my original function and just get a feel for it, I know that it's decreasing here, increasing here, and decreasing here. Okay, so what does that mean? Well, it means that at pi over 3, I'm going to have a minimum, and at 5 pi over 3, I'm going to have a maximum. Okay, so let's make our statements. We can say that f of x is decreasing on the intervals. Well, we've got the intervals from 0 to pi over 3 and 5 pi over 3 to 2 pi. And it's that way because, I'm going to abbreviate, the first derivative is less than 0. There's my justification. My original function is increasing, and this is increasing from pi over 3 to 5 pi over 3 because my first derivative is greater than 0. And then I need to state about the relative max and relative min. Did not leave myself enough room. F of x has a relative max when x equals 5 pi over 3, because the first derivative changes from positive to negative. And then f of x has a relative minimum when x equals pi over 3, for the exact opposite reason that f of x changes from negative to positive. Okay, so the last thing that we didn't talk about again was what our points are, because it did ask for the points. So if we look at our minimum, and I substitute in pi over 3, when I plug that in, it's not going to be pretty. So I get pi over 3 minus 2 sine pi over 3. Sine of pi over 3 is root 3 over 2, so 2 root 3 over 2, so let's be minus root 3. So there's the y value for my minimum. Then my maximum we have it 5 pi over 3. And when I plug that one in, 5 pi over 3 plus root 3. So those would be the points. Okay, how'd you do? Okay, let's look at one more example. Why don't you try example number 3 by hitting pause and then come back and check your work. All right, the first thing that we need to do is we need to take the derivative of this function. So let's go ahead and do that. So this is a quotient rule. So we've got the derivative of the top is 4x cubed times the bottom minus the derivative of the bottom times the top. Oops. Over the bottom squared. So let's simplify that just a little bit. So we get 12x to the fourth minus 3x to the fourth minus 9 over 9x squared. So we get 9x to the fourth minus 9 over 9x squared. Or we get x to the fourth minus 1 over x squared. So factoring, because I want to set it equal to 0, we get x squared plus 1, x squared minus 1 equals the first derivative over x squared. And so my critical numbers, I have critical values or critical numbers when x is equal to positive or negative 1. That comes from the x squared minus 1. I'm not going to consider the negative, negative square root essentially, so I'm not going to worry about those. But then I also have 0. Except what? What is wrong with the 0? Well, 0 is not actually a critical number because it's part of my domain restriction in my original function. So therefore, my critical number is not 0. I'm not going to look at 0. Okay. Now, let's go and make a sign chart. So if we, oops, I'm still on the pointer. If we go back and we call this f prime of x rather, and we include -1 and 1. Now I'm going to test values in there. So if we test -2, for example, first parenthesis will be positive. Next parenthesis will be positive, bottom will be positive. So this will give me a positive value. -1 is 0, 1 is 0. Let's test in between. Let's test 0. I get a positive number, a negative number. Well, it's undefined, so I can't test 0. Okay, come back to 0. I'm going to put that in there. I forgot we were doing 0. Okay, I'm just going to make a mark. Let's test -0.5, shall we? If we test -0.5, this first piece is positive. This next piece would actually be negative. And this denominator would be positive. So I have a positive, negative, positive, which gives me a negative. And then if I look from 0 to 1 and I do 1/2, I just want to make sure there's nothing funky happening at 0 because there might be. If we check a half, positive a half, we would get positive number here, negative here, positive here. So this will be a negative value as well. Okay, but still something funky happens at 0. We know it's a vertical asymptote because the denominator is 0. Let's keep going. Let's look at 2. If we look at 2, this first term will be positive. The next term will be positive. The bottom term will be positive. So then we have all positive numbers here. Okay, so let's look at increasing and decreasing. From my original function, it's increasing to 0. It's increasing to -1. It's decreasing from -1 to 0. Something funky happens at 0. It's decreasing again and then increasing. So I have a relative max at -1 and a relative minimum at +1. So then I can go through and talk about changing signs. So we know that, let's go write this down. f of x is decreasing on the intervals. Decreasing, we're going to go from -1 to 0, and then again from 0 to 1. We know at 0 there's something funky happening, so we're going to let that go. F of x, and the explanation would be the same up above, is increasing from -infinity to -1, union with 1 to infinity would be the intervals increasing because the first derivative is greater than 0. And then f of x has a max at the point -1. Well, let's just put x equals -1 for now, and has a minimum at x equals 1. And the same justification, because it's changing from positive to negative, that's what gives me a max. Or it's changing from negative to positive, and that's what gives me a min. Okay? The points we'd be looking at, if we start with my minimum, I would plug in 1 as the ordered pair. And when I plug in 1, I would get 1 plus 3 is 4 over 3. So 1 4/3 is my min. And then my maximum is going to be at the point -1, which -1 gives me 1 plus 3, which is 4, over -3. And that gives me my maximum. Okay, how'd you do? Let's look at one more example. All right, the figure to the right shows the graph of the first derivative. You guys pay attention to what they're giving you the graph of. So it's the first derivative, the derivative of the function f on the closed interval -2 to 8. The graphs have horizontal tangents at 1 and 5. The first derivative has horizontal tangents. So what they're saying is that this, don't want that. Let's go to a pen. This would be horizontal, this would be horizontal, just so you can visualize it. The function is twice differentiable. What does that mean? Well, if it's differentiable, then this graph is also continuous. What they're saying to us here is the fact that it's twice differentiable tells us that not only is the original function differentiable, which means the original function is continuous, but it tells us our first derivative is also continuous because it's differentiable. And then it says f of 3 equals -2, and that's not on this graph because we're dealing with something a little bit, we're dealing with the first derivative, and that is the point for the original. So the directions say write an equation of the line at to f at x equals 3. So what I want to do is I want to find a point and I want to find a slope. Well, the point we were given, the point was given to us as f of 3 equals -2. Now we need to find the slope. So we need the slope of f. Well, the slope of f is the value of the first derivative. So I know the slope of f is when f prime of 3, which equals 1. So then it becomes a pretty easy equation. Y minus -2, so let's do y plus 2 equals the slope times x minus 3. And there you have it. Whether you simplify that or not, this is fine. Okay, so then it says list the intervals which are increasing or decreasing of my original function f. Well, you guys, I have a first derivative chart here, essentially, right? I have places where I have critical values. Where are those? Well, those critical values are where the graph hits the x-axis, here and here. So my critical values are at 1 and 6. Now, I want to think about what happens. Where is the first derivative greater than 0? Because where the first derivative is greater than 0, we know my original function is going to be increasing. So I can say, wrong utensil. I can say that f of x is increasing where? Right, everywhere that, let's do -2 to 6, because that's where the first derivative is greater than 0. Okay, so where is it decreasing? Using that same idea. We know my original function is decreasing from 6, and all we've got is to 8. So we're going to just say 6 to 8 because the first derivative is less than 0. Okay, so it says find the x values. Next question says find the x value where there is a local extremum and identify the extremum. Justify your answer. Okay, so we're going to go through and look at the first derivative chart. I think is going to be the easiest way to do this. I'm actually going to scroll up. And let's keep the picture there. And if we make a first derivative chart, then we're going to want to test the critical values. And I know my critical values are at 1 and at 6. So if I test 1 into my first derivative, or sorry, something less than 1, say 0, I know that this number is positive. I also know from 1 to 6 is positive based on my graph, because from 1 to 6 it's above the x-axis. And then from 6 on, it's negative. Or 6 on that I can tell. We don't know much past that. It's negative. So here's what I know about my original function. My original function will be increasing, increasing again, and decreasing. Okay, so if there is a critical point, like 1, where there is no change, so no sign change, no sign change in the first derivative, okay, this is called a saddle point, or we can call it a saddle point. That just means it kind of makes like a look a little bit like a saddle, like a place that bounces back to where it was before. If we look at 6 though, what is 6? At 6, that would be a maximum, but why? Well, we know that we have a relative max at x equals 6 because why? The first derivative changes from positive to negative. Okay, so that is the first derivative test. Hopefully you remember some of that. Hopefully it clarifies some things that you didn't remember. Your assignment today is a WebAssign. Obviously the WebAssign is not due for a while, so I would maybe focus on the test that you're taking. And I will see you soon.